In this lecture, we'll discuss the terms relevant to method validation, or the process of showing that a new procedure or an existing procedure applied to a new type of sample meets the intended purpose. To accomplish this, we'll perform some basic calculations to describe concentrations that may fall below our lowest concentration standard. If we had no previous experience with an analytical method, we would begin by preparing a series of standards with concentrations that span our best guess of the range of concentrations we're likely to see in our samples. However, the instrumental response may not be ideal over the entire range of the standard concentrations we've just prepared. If we look at the curve on this slide, we see that we get an instrumental response from our blank, or 0, all the way up to C sub 2, our standard with the highest concentration. Unfortunately, the response over this dynamic range is not linear, so as our standards become more concentrated, we see the instrument response is not proportional to the concentration. For this reason, any sample concentrations that fall within this range would need to be diluted and reanalyzed so that they fall within the linear range. Once we gain confidence in our method, we may find that the entire linear range is not suitable for data reporting. Rather, we have to report only the data that falls in the range of concentrations that meet the degree of linearity, accuracy, and precision required for the analysis. We've seen how high concentrations can limit the range. Let's turn our attention to the low concentration end of the analysis now. We can validate our ability to detect low concentrations by conducting a detection limit study. By definition, the detection limit is the smallest concentration of an analyte that gives an instrumental response significantly different from that of the blank. To conduct such a study, we want to prepare a sample with an analyte concentration at least 1 to 5 times that of the detection limit established from previous experience or found in the literature for a particular method if you're just starting out. After generating a calibration curve, you'll measure this sample containing a low level of analyte at least 7 times to calculate a representative standard deviation. Next, you'll run a blank containing no analyte, just like a sample, against the same calibration curve. Remember that the point of this exercise is to validate when a sample gives a measurement different than a blank containing no analyte. The mean value from this measurement gives us y sub blank. Using y sub blank, we will calculate the signal detection limit as the sum of y sub blank and 3 times the standard deviation from the low concentration sample measurements. 3 times the standard deviation of the sample measurement gives us enough distance between the blank peak and the sample peak to confidently say that, at most, about 1% of the blank's peak area will lie above the detection limit. In other words, we're saying there's enough distance between these two peaks to say that they are giving different values. Next, we'll calculate the detection limit, which is 3 times the standard deviation of the low concentration sample divided by the slope of the line generated from the linear regression of the calibration curve. This detection limit tells us the lowest concentration we can report. If the instrument measures a sample concentration lower than the detection limit, we don't say that we have no analyte present or a 0 concentration. Rather, we say the analysis yielded results below the detection limit, because there may in fact be some very, very low concentrations of our analyte present, but we cannot detect it with the method we're currently using. Finally, we can report the concentration of our samples by subtracting the blank measurement and dividing by the slope of the calibration curve. Now, that was a lot of complicated jargon. Let's step through an example to see how a detection limit study is applied in practice. Suppose that we have run 7 samples with a concentration roughly 3 times that of the previously established detection limit. We find that the instrumental responses, tallied here in nanoamps, gives us a standard deviation of 0.56 nanoamps. Next, we need to run the same number of blanks or samples without analyte. After running our 7 blank samples, we calculate a mean Y sub blank of 1.26 nanoamps. We can use this information to calculate the minimum detectable signal, YD sub L, as Y sub blank plus 3 times the standard deviation of the low concentration sample measurements. That gives us 1.26 nanoamps plus 3 times 0.56 nanoamps for a minimum detectable signal that occurs at 2.94 nanoamps. Next, we need to construct a graph using higher concentration standards, perform the linear regression of the scatter plot of those data points, and use the resulting slope in our calculation. The detection limit for the analysis is 3 times the standard deviation of the low concentration sample measurements divided by the slope of the calibration curve, 0.229 nanoamps per micromolarity. Running through the calculation, we discover that the lowest quantity of analyte that can be detected by this particular instrumental method is 7.3 micromolar. Anything less than this amount must be reported as below the detection limit rather than as a zero value. Alright, let's grab the values we just calculated for Y sub blank, Y sub DL, and the detection limit to find the concentration of another sample run against the same calibration curve. Suppose our sample has an instrumental response of 7.0 nanoamps. What concentration can we report? Using our equation, Y sub sample minus Y sub blank equals the slope times the sample concentration, we can rearrange to solve for the sample concentration. Y sub sample is 7.0, Y sub blank is 1.26, and our slope is 0.229 nanoamps per micromolarity. Running through the math, we get a sample concentration of 25.1 micromolar. Since this value is well above our detection limit of 7.3 micromolar, we can report the actual value. We've just seen how to calculate the detection limit as 3 times the standard deviation of the low concentration samples. While this is the lowest concentration that we can reliably distinguish from the blank, the instrumental response is still fairly low and may not be as accurate as we would like. While it's not unlikely to see detection limits reported in research articles, especially where we're pushing the boundaries of our instrumentation, for the purposes of government or industry reporting, it's far more likely to encounter the lower limit of quantitation, which we typically call the LOQ. The LOQ is 10 times the standard deviation of the lowest concentration samples divided by the slope of the calibration curve. This is the smallest amount that can be measured with reasonable accuracy. Even so, regulations may not require concentrations exceeding the LOQ to be reported, but rather rely on the published reporting limits for the particular industry.